Hello students, we are going to continue our discussion on the first law of thermodynamics, and now I am going to emphasize upon the two energy functions which have been introduced through the first law of thermodynamics. The first one is internal energy, and the second one, which will be introduced to you today, is enthalpy. So let us go ahead and see what information that we get from first law of thermodynamics about these two energy functions. So the first law of thermodynamics, as we have already seen, tells us that for an infinitesimal change in state, U is a state function that undergoes an infinitesimal change in its value, and this is du. And by doing an external perturbation on the system, we can carry out this infinitesimal change in the value of U. And if I supply dq, that is the infinitesimal amount of heat to the system, or if I allow the system to perform dw amount of work, then it would, during this change in state, there will be the corresponding change in the internal energy, which is du, and du would be equal to dq plus dw. And similarly, for a finite change in state, I will show that the change in internal energy will be equal to the sum of the total amount of heat exchanged between the system and the surrounding and the amount of work done by the system or the amount of work done on the system. Now, the question is, if I propose the concept of internal energy, then I should be able to measure it. And the proposal of first law of thermodynamics says that it cannot be measured. Absolute value of internal energy cannot be measured. But at the same time, it also says that during the change in state, I can make the system interact with the surroundings and thereby measure the change in internal energy. So what kind of experiment will you do to measure the change in internal energy? I'm going to use the first law of thermodynamics once again. Now, if I have a constant volume process, in that case, I understand that W is equal to 0 and delta U would be equal to QV, that is the amount of heat exchanged between the system and the surrounding when the system is undergoing a change in state under isochoric conditions. And this type of experiment is carried out using a calorimeter, where the different properties of the calorimeter are calibrated and well known, and therefore you can actually estimate Q of V from the known properties of specific heat of the materials of the calorimeter, and you can note down the temperature change during a process, and from there you can find out what QV is, and correspondingly you can find out what delta U is. Alternatively, one can think about an adiabatic process whereby, by definition, Q is equal to 0. Therefore, if you have any method of measuring the quantity W, in that case you can find out what delta U is. And so if you can estimate W as PV work, in that case you can immediately estimate delta U in that particular process. So this is how to measure the change in internal energy from an experimental perspective. And as you understand, both the quantities that I am talking about here, Q and W, these are experimentally controlled parameters that I can change under laboratory experimental conditions. Next, let us ask the question of how this quantity, internal energy, will change with temperature. So for this purpose, let me think of the simple situation where I am heating the system at constant volume. So this is a schematic diagram of a typical system that I will be employing here. So as you see here, some gas is contained within this cylinder, which is surrounded on three sides by insulated walls. The bottom layer, the bottom wall is a conducting wall, and therefore if I supply heat, it will absorb heat through this lower wall. And I can find out the temperature, increase in temperature of this working system by looking at the thermometer which is inserted into the system. Please also note that the top wall of surrounding my system is locked in position by using this set of locking pins. And therefore, if I am heating my working substance, I am doing so under constant volume. And here I can find out the amount of heat supplied to the system here by knowing the mass of the system involved, including the mass of the calorimeter, the specific heat of the system, including the material of the thermometer as well as the calorimeter. So this is a schematic representation of a calorimeter, and also by noting down the change in temperature when you have supplied some amount of heat. So once I know this, then I can indeed find out what in this case delta U is nothing but QV. Now, if I go a little bit forward and try and understand this question, that there are many system properties like temperature, pressure. Under different conditions, I can study the variation of internal energy with these system properties. How do I determine these variations? So for that purpose, let me consider an infinitesimal change in internal energy whereby I probe du in a closed system. Now let me start by saying that U in general is a function of temperature, that is a temperature T of the system, volume V of the system, and the number of particles present in the system. And then I can very easily write down that for a closed system where n is a constant number, then du must be dependent on dt and dv. So what I mean by this is my initial equilibrium state is given by T, V and N, say. And then I introduce an infinitesimal change in state whereby the temperature of the system becomes T plus dt, the volume of the system becomes V plus dV, and N remains constant. Since U is a function of the values of T, V and N, therefore as T changes to T plus dt and V changes to V plus dV, U will also undergo a change in value. Let us say that the new value of U is now U plus du. And then we are asking the question, how does du depend on dt and dv? So this is the expression that I have given you here that follows from the definition of U as a state function, or in other words, du as an exact differential. If this is so, here I identify as response functions of the system the two quantities Cv, that is the specific heat at constant volume, which is defined as this first partial differential that appears as a coefficient of dt in this expression, and also internal pressure pi t, which is given by this partial derivative variation of U with respect to volume under isothermal condition, which appears as a coefficient of dV in this expression. Therefore, I understand that here during this change in state, I can control dt and dv from outside. And the rate at which the system responds to these external perturbations are given by these partial derivatives, and therefore they are called response functions of this system. So they quantify the amount of change in property in response to an external perturbation under the given experimental condition. Therefore, if I use these definitions of these response functions, I can very easily write down that in general, du is going to be Cv dt plus pi t dv. And if I integrate over if my system goes from an initial state 1 to a final state 2, I can integrate on both sides, and I can write down that delta u is nothing but u2 minus u1, and that is given by Cv into delta t plus pi t into delta v. Okay. Now this is a perfectly general expression. I can always prepare an initial equilibrium state at a given temperature, volume and number of particles. I can very easily change the temperature of the system such that there is delta T amount of change in temperature, there is delta V change in volume of the system, and then using this expression we can say what would be the corresponding change in the system internal energy, which would be given by delta u Cv into delta T plus pi T into delta V. Now moving ahead, I can also think of varying internal energy with volume. Now by definition, I have said that del u del V T is equal to pi T. So what kind of experiment am I talking about? I am talking about an experiment where I am going to maintain isothermal condition. From outside, I am going to change the volume, and I will be looking at the corresponding change in internal energy. And this response function is called an internal pressure. And in order to understand how we can measure this internal pressure, let me use this particular treatment. Since I am in a closed system, I will not explicitly write down the dependence on n, but rather use this shorthand notation that u is a function of t and v. And then if I use the cyclic rule, I can very easily write down that this is the partial derivative that I am looking for. So using this expression, I can write down del u del Vt, and the next two terms follow from the cyclic rule, and this should be equal to minus 1. Therefore, what I find is del u del Vt is nothing but negative of this partial derivative and this partial derivative. Now, do I know what this partial derivative is? That is nothing but the specific heat of the system under constant volume condition. And now I define this partial derivative as the Joule coefficient and give it this notation. So let me say mu j is del T del V u and Cv is del u del T V, and correspondingly I can define the internal pressure as negative of the product of Joule's coefficient mu j and the specific heat at constant volume Cv. Therefore, if I want to know what pi t is, I should be able to measure mu j and Cv. Now for Cv, the specific heat, a very large number of data are available for a wide variety of systems. But then what is mu j? Now mu j, if you look at the definition, you understand that mu j can be measured in an experiment where the total energy of the system is fixed. You will vary the volume of the system and you will look at the resulting change in temperature. Then if you can measure the rate of change of temperature with respect to volume under this constant energy condition, you should be able to measure mu J. So this is exactly what was measured in Joule's experiment. Now, I will come back to this later, but let me once again use the same set of expressions to find out the variation of volume at constant temperature. And here, what I find is as follows. So this is nothing but the Joule's experiment, and what I have done is I have prepared the system under initial equilibrium condition such that the entire setup is insulated and therefore no external energy is being supplied from outside. Now my system is comprised of two bulbs, one here, one here. And one side of the bulb is filled up with an ideal gas, the other side is a vacuum. And the two bulbs are connected by a valve that can be opened, but it is closed in the initial equilibrium state. Now have a look at what Joule's experiment tells us. In the Joule's experiment, after you prepare this initial equilibrium state, what you do is you open this valve. What will happen? There will be expansion of the gas against zero pressure. Consequently, the observation that was made here was that the gas expanded, and in the final equilibrium state, the gas filled up the entire volume available to it, which is the volume of the two bulbs and the connecting pipe between them. And the observation was there was no change in temperature associated with this expansion of the ideal gas against zero pressure. And therefore, I can very quickly understand from here, since it is a free expansion, P external is equal to 0 for the expansion of the gas, therefore dW equal to 0. The entire experiment was carried out under adiabatic conditions because no energy was supplied during the change in state. Therefore, I can say that dQ is equal to 0. And therefore, the first law of thermodynamics tells me that du should also be equal to 0. Now, think about the way we have visualized the dependence of U on changes in temperature and changes in volume. In this case, what I have is then, since dt is equal to 0, therefore du must be equal to pi t into dV. If that is so, then this quantity must be equal to 0. Now in this experiment, did I have volume constant? The answer is no. Once I opened the valve, the gas could undergo an expansion. Therefore, dV is not equal to 0. Therefore, I would say that when there is no change in temperature of this ideal gas, then pi t must be equal to 0. Now, what is pi t? Pi t is del u del Vt for by definition. Therefore, I understand for an ideal gas, del u del Vt must be equal to 0, or the internal pressure of an ideal gas is equal to 0. So in that case, I would always write that for an ideal gas, du is equal to Cv into dt for any infinitesimal change in state accompanied by a non-zero change in temperature. And this also tells me that for an ideal gas, U is a function of temperature and temperature only. But please remember that this is valid for an ideal gas. Now, if I have a real gas instead, what do I expect? In this case, by the design of the experiment, once again, du would be equal to 0. But during this isothermal, irreversible, free expansion of the gas, I would still have du equal to Cv dt plus pi t dV. But since by the design of the experiment du is equal to 0, I can immediately write down that for a real gas, Cv dt plus pi t dV must be equal to 0. And this would tell me that in this case, dt would be given by an expression like this. Now you understand, if pi t is equal to 0, then dt should definitely be equal to 0, which was the case of an ideal gas. But if pi t is not equal to 0, what I can say is, think about what pi t is. Pi t is nothing but mu j into Cv with a negative sign. If I put it back here, then what I do is I can write down dt is equal to mu j into dV. So if you see some finite change in temperature, in that case you can very easily find out what mu j is. That would be, for a finite process, delta T divided by delta V. And then I can say that pi t I can actually measure by looking at what mu j for that system is and what Cv for that system is. And for a real gas, this way you can find out the internal pressure. Now, therefore, I can also think of variation of temperature at constant pressure and think of how internal energy varies under such condition. So I will start from this expression once again, which is a perfectly general expression. And now I'm going to vary temperature at constant pressure. So which partial derivative am I looking for? I'm looking for del u del T P. And if I take a derivative on both sides with respect to T under constant pressure, this is what I will get. And here I know pi t is equal to minus mu j into Cv. Therefore, del u del Tp, I can take the Cv out and this is what remains in the bracket. Now, if I want to find out how much change u undergoes for variation with temperature and constant pressure, I will have to know the value of Cv, value of mu j, and also the value of this quantity del V del T P. This is another response function of the system, and we define it as the isobaric expansion coefficient. So how do you measure this isobaric expansion coefficient? All you do is look at the definition of alpha. Here this is 1 by V del T P. So you are supposed to carry out an experiment whereby you will be changing the temperature of the system under isobaric condition, and you will be looking at the change in volume, actually the fractional change in volume. Okay, so if you plot the fractional change in volume, that is delta V by V, against temperature under constant pressure, in that case it will depend on the system how the system will change with temperature, and you can find out the slope of that curve, and that will give you alpha. And alpha is also a property that can be measured in laboratory and is widely tabulated for a wide range of systems. And now I can rewrite that del u del Tp is Cv into 1 minus alpha mu j into V. So now you understand that it is possible to find out the value of the right-hand side for a given system. And therefore, you can find out what del U del T P is. Now, so summarize what we have learned from internal energy. We understand that internal energy U of a system is the total kinetic and potential energies of all its constituent particles. Of course, thermodynamics doesn't give you any idea about what it actually is. So this is a concept which followed mainly from our understanding of the microscopic picture of the system, and it is possible to correlate the total energy, the total kinetic and potential energy of a system to the internal energy under given conditions. Now we understand if I have an isolated system, then the system is not interacting with its surrounding, and therefore the change in internal energy is going to be zero if the system is maintained at equilibrium. Therefore, U is a constant for a given isolated system. And if the system interacts with its surrounding, and if it undergoes a change in state, whereby it passes from an initial equilibrium temperature T to T plus dt, and it goes from an initial equilibrium volume V to V plus dV, there will be a corresponding change in internal energy, which is du. And du will depend on dt and dv, and their coefficients will be called the response functions of the system, and these are known as the specific heat at constant volume and the internal pressure. The first law of thermodynamics tells us there are two ways of changing U. One is by supplying heat Q, or by making the system exchange work with the surrounding, where work is given the symbol W. And for constant volume processes, we can actually measure the change in internal energy directly by knowing the amount of heat supplied to the calorimeter in which our system of interest is contained, if it registers a temperature difference of delta T by supplying this amount of heat. So now we have learnt the details of what thermodynamics tells us about the concept of internal energy. It also gives us the concept of enthalpy. In the next lecture, I will introduce to you the concept of enthalpy and see how it extends the scope of internal energy and takes into consideration what happens if I heat the system under constant pressure. Thank you.